Hey guys, Greaves here. Pretty excited to have a new, I'm not sure what to call this, apparatus which holds my iPhone. So we're going to give this a shot. Let me know how this works out, if you can see it, etc. Just send me a little message if it's bad. Okay? All right, so we're going to talk about waves. Right now I've already written it out here. What is a wave? And by the way, this is not going to be easy for me to describe everything. I'm going to send you some YouTube video links, which I'd like you to kind of watch as well, to do the best to visualize what I'm trying to explain. All right? So what is a wave? Well, it's a vibratory disturbance which is going to transmit energy. All right, I've already have the energy written here, but just be aware. It's just energy. It does not move matter, right? Matter is not going to be moving around. So matter, no. Energy, yes. Right? We'll get to that in a second, right? From one place to another. Okay? So let's take a look, right? Hopefully, right, you've looked at the first video, which I'm going to instruct you to do when I send this out, right? So let's take a look at something. First, we need to take a look at a couple of types of waves. And the first type of wave, which we're going to look at, is called a transverse wave. So what by definition is a transverse wave? Transverse wave is a wave which is described by, I should say, let's put it this way, points on the wave move perpendicular to energy transfer. Right? In the first video you saw, right, you should be looking at some slinkies, right, and they had them wiggling around. So let me give you a better idea, hopefully, of what I'm talking about. It's just a visual. Suppose you're looking at a water tank, right, a fish tank, right, looking from the outside of the fish tank, right. So here's the fish tank. Well, obviously we're going to have water in the fish tank. So here is the surface of the water. So here is water, right? Here's the air. Well, what happens if I drop a pebble in there? So if I drop a pebble, right, plop right there, what's going to happen is, well, you know, the water, right, is going to be kind of like, look like this, right? And on this side, the water is going to kind of, so the water waves, right, if I drop the pebble right in there, the water waves are going to propagate away from, right, where I drop the water. And what happens is, right, look what happens, right, the waves, right, so this part up here, right, the water is going to get high. This wave part here, the water is going to get low, right? So here would be air again, here would be water, and that would propagate outward. So this here, right, where the water is level, I'm going to say is my equilibrium position, right, original equilibrium position, nothing's there. Okay, I mean, it's not moving, it's just where the boundary between the water and the air is. So hopefully that you get that idea by looking at the video. I'm going to send you another one. I'm going to ask you to see another one after this, which might give you another little better idea. Now, what's going to be weird is we're going to try very hard to represent this stuff on a piece of paper, okay? And here, right, I have a graph, right? It's not really a graph like you're going to X and Y coordinates or anything like that. It's just how we now are going to kind of visualize a wave, right? A wave. So once again, here is, think of this imaginary, like here is going to be my water boundary, right? I should say the boundary between water and air, just an analogy, right? So here is my equilibrium position, right? Right, there's my equilibrium position, right? And here's the water, here's the air. Suppose I drop that pebble in there, right? What's going to happen is we're going to get something that looks, hopefully I'm drawing it okay, right? That looks like this, right? And this is going to be my little, right, you know, here is the water that kind of went up. Here's the air, right? The wave went down. Here's the water that went up. So here's all my, right? Hopefully you can see that. And this is, obviously, we're just going to, when we do this on a piece of paper or you look at it, you're just going to be seeing, right, this kind of sinusoidal wave here, okay? So let's take a look at some characteristics. Number one, what did I say? right? Energy, this is an example of a transverse wave. Why is it transverse? Well, in this particular case, the energy, right? I'm going to say energy is moving. In this particular case, we're just going to say it's moving to the right, right? If it's moving to the right, right, what about the points on the wave? Well, let's go back to this line right here. Here's my equilibrium position. If I were to take a leaf and kind of put the leaf right on the water surface, it's just resting there, right? Well, now, believe it or not, as the wave goes by, that leaf or that object, whatever it is going to bob up and down on my surface. So let's suppose I say, here's my point. Let's call it point P. Which way is this point allowed to move if this is in fact a transverse wave? Well, if this is point P and it's a transverse wave, we said before, points on the wave move perpendicular to energy. And perpendicular in this particular case, if this is to the right, perpendicular would mean it can only move up or what? Down, right? So, transverse wave. Right? Okay, so there are some characteristics here of this wave that I want you to take a look at. Right? And I'm going to just have to flat out tell it to you. Okay? Well, one thing that we can look at is something called a wavelength. All right? Wavelength is given to us by the Greek letter lambda. Right? Right? So what by definition is a wavelength? Now I'm going to introduce some stuff. Right? We haven't gotten there yet. It might take some time, right? But I'm just going to give you the definition, okay? It is the distance needed to complete one cycle. What does that mean? All right, well, by the way, that's going to be, it's a distance, isn't it? So that better be in meters. So what does that mean? Well, if this wave is moving to the right, and this is, say, the leaf on the water, one cycle would be, well, it's going to go up, then it's going to come back down. I know it's actually weird. It's going to go up, past to where it was at this instant in time, down and back. So up, all the way down, and back to its original position. So this is what we call a wavelength, right? Meaning the distance needed, right, for this point on the wave to complete one cycle. We'll get into more of that tomorrow or the day after, what a cycle is, etc. Just right now I want to do some basics. 2, amplitude. What is an amplitude? By the way, we just characterize that as A. Okay, so what is an amplitude? All right, well, the amplitude by definition is my maximum displacement from rest position. By the way, that is also going to be in meters. So let's see. If here is my equilibrium position, right? This particle is going to wiggle up, down, up, down. So this here would be 1 amplitude. By the way, that would be maximum in the upward direction, which also means it's going to also go down, right? Big mistake is, hey, what's this here? Well, that's 2A, okay, not an amplitude, okay? A couple other things. It's important later on, but it's just kind of something you should be aware of. What is this point here? We call this the crest. This would be the top of the wave, okay? How about down here? Well, this is called a trough. If that's the top of the wave, the trough is the bottom of the wave, okay? So here are some characteristics of a transverse wave, something that you should be aware of, okay? So I'm going to move to another piece of paper, and we're going to look at another. Oh, by the way, let me come back. Sorry, my bad, okay? Let me give you some examples of a transverse wave. What's an example? Haven't gotten there yet, but a light wave is an example of a transverse wave. What else? Well, you've all been at the beach, right? We live on Long Island. So a surface water wave is also a very good example of a transverse wave, okay? So let's go to another type of wave that we're going to be asked to know about in physics, okay? That's going to be a longitudinal. So 2, longitudinal. Right? So what, by definition, is a longitudinal wave? Well, if a transverse wave, right, the particles move perpendicular, right? A longitudinal wave, points move parallel to energy transfer. Okay? Now, hopefully you saw that video and the gentleman showed you a longitudinal wave, right? So I'm going to go back to that slinky that he probably had, right? So everyone's seen that slinky, right? You've played one at home, take it out of the box, roll it down the stairs. 2 seconds later, it looks like spaghetti, right? So there's a slinky. What would happen if I push on this slinky? If I take it and I kind of push it, push it, push it, push, right? Well, what's going to happen is, as I push, I'm going to compress maybe just this area right here. So what's going to happen is you might get something that looks like this, right? So there would be, hopefully, if you can see it, right? Example of a longitudinal wave. Here's my energy, right? What about the points on the wave? So if I call this a point right there, there's point P. What's going to happen? As the wave moves from left to right, this point is going to go to the right, and then it's going to come wiggle back and forth, right? So here, by definition, is a longitudinal wave. Now, you might be able to look at something, right? Now, let's see if we can make some comparisons. In a transverse wave, we had wavelengths, etc. Believe it or not, there is a wavelength here as well, right? By the way, I think I need to go back, right? I think I need to go back, right? I made a kind of little bit of a mistake here. Not a mistake, but I didn't really actually show you where a wavelength is. So let's go back here for a second. Let's take a look at this transverse wave. Well, the wavelength is the distance needed to complete one cycle. Well, where would a wavelength be? Well, I've told you that here's a crest, here's a trough, right? Well, let's take a look. Well, believe it or not, right? This distance here, right, from trough to trough happens to be a wavelength. Not only that, right, this distance here from crest to crest happens to be a wavelength, okay? And there are many other here as well. I'll just point out these two here as well, okay? So let's go back to my longitudinal wave, okay? So like I just showed you right there, I showed you where a wavelength is for a transverse wave. Where could a wavelength be represented, right? Between these two compressed areas. Now, these are kind of, maybe not so much that you need to know, but what do we call this? Well, as I just said before, it was compressed, so this is called a compression, right? It's where the particles on the wave are squished together, compression. How about over here? Well, believe it or not, this is where things are separated. It's called rarefaction, right? It's rarefied, so that's a rarefaction. So these are kind of analogous to my crests and troughs, right? So compression to compression, wavelength, right? Rarefaction to rarefaction, also a wavelength. Is that okay? So examples of these. Well, the big one that we're going to look at is called sound. Right? The fact that you're hearing my voice, right? It is in fact a wave. It is transmitting energy from one place to another, and it happens to be a longitudinal wave. All right? So there's a longitudinal wave. Now, something that is important, right, for in the next couple of lessons, right, it's looking at a wave, right, and seeing, hey, are the points moving up and down, right and left, etc. So I'm just going to call this determining direction of points on a wave. Okay? What I want you to do now, at this point, I want you to stop the video. I want you to take a look at this, my video that is, and I want you to take a look at the second video link to YouTube, right? He does a pretty good job of showing stuff, a little setup better than I can do here at home. So take a look at that, all right? Now, all right, now we're back, right? So let's take a look at what I mean by that. Well, here is my representation of a wave. Here's my equilibrium position, right? Right? Air, water boundary, whatever you want. And let's put a wave, drop the pebble in there, and there's my wave, right? So there it's going to propagate, right? Away from that position right there, right? So let's take a look at, you know what, just for argument's sake, I'm going to take a look at this point, and I'm going to take a look at this point. Okay, well, what are these guys? What direction are these 2 points moving at this point in time? Well, what type of wave am I looking at? Well, I'm looking at a transverse. So right now, the only 2 possibilities for these 2 points are it could be going up and it could be going down. It's a question mark, a question mark. So that's the only 2 possible directions that these 2 guys could be making, right? Well, what is it? All right, well, I'm going to give you a little technique now on how to figure out at this instant in time, which direction are these 2 points moving? And let's go back. Let's call this point number 1. Let's call that point number 2. All right, so technique that I want to introduce you to is, I know it's going to sound a little crazy here, but I want to draw where the wave is, right, in the next instant in time. What do I mean by the next instant in time? I don't know, 10th of a second, 20th of a second, 100th of a second. It really doesn't matter, right? All I know that as energy moves from left to right, energy, the wave is going to propagate to the right, okay? So how am I going to make a nice little drawing? All right, so we're going to take points. I want you to just watch what I do. Make little points on the crest and trough, right? And since it's moving to the right, I want you to just draw my dots over there. And why do I make them? Because I just want to have a nice little outline. Where is the wave going to be in the next instant, in time? All right, so hopefully you can see my dotted lines, right? And by the way, we don't need to be Picasso here. It's not AP art. We're just kind of taking a look. Hey, where is the wave going to be, right, in the next instant in time, right? So there's where the wave is moving. Now, let's think about these 2 points, 1 and 2. Let's say that they were leaves sitting on the surface of the water. They must always remain on the surface of the water, right? So as the waves moves by, right, the particles are going to wiggle up and down, right? So this dotted line represents where the surface of the wave is going to be in the next instant in time. So there's my particle. Well, it must remain on the surface. So which way does this guy going? Well, it must remain on the surface, and the surface now looks like it's down there. So at this instant in time, point number 1 is moving what? Down. How about point number 2? Well, it must remain on the surface. And where did my surface go? Well, number 2 is going which way? Up. So here's one technique to determine which way the points on a wave are moving at any given instant in time. Draw the wave some instant in time later, right? See where that wave is, and the point must stay on that surface. Okay? Another technique, right? Well, remember the water waves when you go to the beach? Look, here you are. You're out in the beach, right? You're on the beach. You're in the water. There's the water. There you are, right? What's going to happen, right? Here comes a water wave moving towards you, right? As the water wave moves toward you, which way do you go? Think about this. As the wave is moving towards you, you're going to go what? Up the front of the wave, down the back of the wave. Up the front of the wave, down the back of the wave. Right? So let's take a look at another example of that. Here's a wave, right? I really call this the leading edge, trailing edge method, right? So if it's moving this way, let's just take a look at from this trough, to this trough, right? Which way are all the particles moving on this side? Well, the wave, There you are sitting in the ocean again, right? The wave is coming towards you. You're going to go what? Up the front of the wave. And what? Down the back of the wave. Up the front of the wave. Down the back of the wave. So I kind of call this leading edge, trailing edge. The leading edge of the wave, front of the wave, we go which way? Up. Back of the wave, trailing edge, down. So just another way to give you an idea of what's happening with the points of a wave. All right, last thing for today, okay? Like I said, these techniques, these things that I'm showing you now, are really going to be for later on, right? I just got to lay the groundwork, right? Now, it's going to be a little abstract, but I want to talk about phases of waves. All right, so what do I mean by that? All right, so there are points on those waves, right? So let me go back to this wave right here. I can look at any individual point on this wave, right? And every individual, I should say, they're an infinite number, right? And they're doing different things at different times, right? But there are some waves or some points on these waves share some characteristics. And if they share some characteristics, we say that they're in phase, right? So let's just talk about how I determine whether 2 points on the same waves are in phase. Okay, so they have to have one same velocity. So remember, what is velocity again? Well, velocity has a magnitude, speed, really, right? This is the speed, right? Magnitude of speed, and a direction, right? So same velocity, but remember, velocity has 2 things, speed and direction. Well, I will tell you now, the speed of all the points on the waves are exactly the same. So I'm not worried about the speed, but I am concerned about the direction of the points. Remember, the points can be moving up and down. So phases of waves, if 2 points are in phase, they share that they're going in the same direction, meaning up or down. What's next? Well, they must have the same displacement, meaning amplitude. Is it above the wave of the equilibrium position or below? So we can figure out if 2 points are in phase if they have the same direction, up and down, same displacement. So let me tell you what I mean by that. Let me give you some examples. So here is a wave, right? And we're looking at the pebble has already been dropped into the water, and it is kind of, right? You're just looking at that fish tank again, right? And it's on its way. We took a picture, right? There's the picture. Right, so let's call this point A, point B, C, D, E, F, G, L, M, N, O. Let's just call that P. You can't do anymore, right? So there are those points on the wave. So what do let's take a look. Let's just, for argument's sake, let's take a look at E and I. E and I. Are E and I in phase? E and I. Are they in phase? So the answer is yes. Or what? No. All right, so what do they have to have? Well, they have to have the same direction, right? And same displacement. Well, one I can answer pretty quickly, right? They are both on the equilibrium position, so they do share the same displacement. But what about, are they going in the same direction? Well, unfortunately, right, we're going to have to do our technique. We're going to have to move our wave, right? Look at our wave at some instant in time later. All right, so there are my dotted lines. So let's take a look. Remember, E must be on the surface. So E is moving up, but I is moving what? Down. So are E and I in the same, are they in phase? The answer is no. All right, why? Because they don't share both displacement and direction. Let's take another one. You know what? Let's take a look at A and I. You know what? I'm going to look at A and I. Since I know what's going on, A and I. Let's move that over, right? So A and I. Are these in phase? Yes or no? Well, do they share the same displacement? Let's do displacement, right? Obviously, because they're in the equilibrium position at this instant in time. And yes, they do. Are they both going in the same direction? Well, if I continue my wave, A is moving down as well. And lo and behold, yes, they do. Okay? Now, we can do a whole bunch of them. Let's take a look. C and K. C and K. I got to move that over. C, do they have the same displacement? One amplitude? Yes, same direction. Well, there's my red line, which is going to be my wave some instant in time later. Down and down. So C and K are, in fact, in phase. And we could kind of go through, how about G and O? G and O are also in phase. What about F and H? Well, no. By the way, they are the same displacement, right? But they are going in opposite directions. So no, those are not, right? Believe it or not, there's a much easier way to figure out if points on a wave are in phase, right? So we say points on a wave are in phase if they are, ready? Let's take a look. What did we say? C and K. How far away is C and K? Well, going back, it happens to be from crest to crest. That's a wavelength. What about A and I? That was also a wavelength. G and O. That's also a wavelength. So points on a wave are in phase if they are one wavelength, two wavelengths, three wavelengths, ... apart. Okay? So this is one way we can figure out a waves are in phase. Okay? So that's it for now, guys. I will send you a couple of multiple choice problems on Infinite Campus just to take a look and make sure we're all in the same spot. All right? Email me with any questions. All right, guys? Bye-bye.